All right, so in the second half of the 7.2 notes, we're going to talk about solving basic exponential equations. So first things first, when we have an exponential function, it's where we've got some kind of a variable up in our exponent. When we want to solve that, we really have two options that we can go through to algebraically solve it. The first is to use what's called a logarithm. We're going to be talking about those here in the coming days. So we're going to get to that and talk more about that when we get there. Right? The use of logarithms is typically done with more complex equations where I can't solve using the simpler method, which we're going to talk about here. So the second way we can do that and solve one is something called the exponential equality property. Okay? So the equality property for exponential functions states that if I have two exponential functions, b to the x sub 1 and b to the x sub 2, or b to the x equals b to the y, if the bases equal, okay, the bases must be equal to one another here. So if I have b to the x equals b to the y, this happens if and only if x equals y. So those two exponents equal one another. So essentially what we're talking about here is if I can take an exponential equation and write it using the same base on both sides of my equal sign, then if I can write using the same base, I can just simply set those two exponents equal to one another once they're both represented with the same base. If, however, I cannot write both sides using the same base, this doesn't help us at all, and then we need to use a logarithm to go ahead and solve it. So let's take a look at a couple examples here. And the first two I have typed out for us, but I'm just going to talk through them. So here I've got an exponential function, 3 to the 2x minus 5 power equals 3 to the x plus 3 power. Okay? Because the bases are both equal to one another, right? I have nothing being added, subtracted to either one of those exponential bases. I have nothing times any of those exponential bases. I simply have an exponential to a power on each side and nothing more. Okay, and those exponential bases happen to match. Because they match them, I'm able to set those two exponents, 2x minus 5 equal to x plus 3. And from here then, I solve whatever I have. In this case, it's a linear equation. So we could subtract x on both sides, then add 5 on both sides, and we get x equals 8. So for the second example that I have down here, I have 2 to the 3x minus 1 equals 2 to the 1/3 x plus 5. Because, again, these exponential bases match, there's nothing else happening to the exponential. Again, nothing added, subtracted, multiplied, divided, right? So I can set these exponents equal to one another. So 3x minus 1 equal to 1/3 x plus 5. And from here now I solve, right? So if I subtract 1/3 from both sides, I would have 8/3 x. And if I add 1 to both sides, equals 6. If I multiply both sides by my reciprocal, 3/8. We're going to have x equals 18/8, or x equals 9/4. Okay? Let's take a look at another one. Now here, I've got a slightly different issue, right? I've got 3 to the 2x plus 3 power equals 27 to the x minus 1. Now, if you remember back to exponent rules, right, and you should have seen that in the notes in the previous lesson or two. If you have something, say, x to the a power raised to the b power, so if I have an exponent raised to another power, or a power to a power, remember that we multiply those exponents, okay? So if I had something and I want to rewrite it or re-represent it in a different way, I'm able to do that using this power. So here, what I want to do is I want to look preferably at the larger of the two numbers. I want to ask myself, is there a way I can write 27 as 3 to some power? I want to try and make that base smaller. Okay, and ideally I want to make it match this. There are going to be times where I have to rewrite both, all right? But hopefully you would agree that 3 to the 3rd power is 27. So let's rewrite that right-hand side. So I have 3 to the 2x plus 3 equals 3 to the 3rd power to the x minus 1 power. Now, remember from over here that if I have a power to a power, it's those exponents multiplied together. It's the product. It's the product of the entire exponent. And even though they're not written around this exponent here, I need parentheses because I have to distribute. It's a common mistake. We have a test question that's going to look at this, and if you forget parentheses, you're going to get it wrong. Okay? So when I distribute them, what I really have here is 3 to the 3 times x minus 1 power, or 3 to the 2x plus 3 equals 3 to the 3x minus 3 power. All right? Again, I have like bases. I can set those exponents equal to one another now. So we have 2x plus 3 equals 3x minus 3. So I'm going to go ahead, I'm going to move, subtract 3x on both sides. I'm going to have a negative x on the left, and when I subtract 3 equals negative 6, or x equals positive 6. Okay. On the next slide, I've got this all typed out, all right? Same thing, just typed out instead of worked out, all right? So we're gonna go through, we're gonna try a couple more of these just to make sure we're on the same page. So here we have 16 to the x plus 1 power equals 1/32. Now, another exponent rule that we're going to have to talk about, and here we're going to have to manipulate both sides. But remember, x to the negative nth power equals 1 over x to the nth power, right? So I can deal with fractions using negative exponents. Okay? So here, I want to look and think and ask, can I rewrite 16 and 32 using a common base? They are both 2 to a power. 16 is 2 to the 4th. Simple, right? Here we get 2 to the 4th to the x plus 1 power. And again, I need those parentheses as a placeholder. 2 to the 5th is 32. But because I want 1/32, I need this to be 2 to the negative 5th. So on the right, we're going to have 2 to the negative 5th power. Now again, let me simplify here. I'll distribute the exponent here. I have 2 to the 4x plus 4 equals 2 to the negative 5th. Again, I have like bases, nothing else happening to them. So I'm going to set those exponents equal. So we have 4x plus 4 equals negative 5. And if we go to solve, I'm going to subtract 4 on both sides. I'm going to have 4x equals negative 9, or x equals negative 9/4. If we go to our next example, I have 4 to the 2x plus 2 equals 8 to the x minus 1. Again, I can't write 8 as a power of 4 directly here. Just doesn't work, okay? But they do have a base that's common. They're both also, in this case, powers of 2. So the 4 is 2 squared to the 2x plus 2. And the 8 is going to be 2 to the 3rd to the x minus 1. And again, don't forget your parentheses around that exponent. When I simplify, then I have 2 to the 4x plus 4 equals 2 to the 3x minus 3. I have like bases, and I can now set those exponents equal to one another. So we're going to have 4x plus 4 equals 3x minus 3. And when I go to solve, I'm going to subtract 3x on both sides. I'm going to have x equals, and when I subtract 4 on both sides, x equals negative 7. Now let's take a look at one more example. All right. And again, I'm kind of working our way through some of the exponent rules that are going to pop up in some of these problems, or little twists based on exponent rules that you may or may not see in certain problems. So again, here I've got 3 to the x plus 1 times 3 to the 3x minus 3 equals 27 to the x minus 1. And hopefully at this point you say, well, 27 is 3 to the 3rd power. You're right, it is. I agree, so let's do that. All right, so I have, instead of 27, I have 3 to the 3rd power, all to the x minus 1 power. Now what do I do on the left? I have to write this as a single exponential base. Well, what would you have done if we had x, say, to the a power times x to the b power, right? If I have like bases multiplied together, I add those exponents. Here I have a like base. It is 3. I'm going to add those exponents. So when I do that, I'm going to have 3, and let me give myself a little bit of room, 3 to the x plus 1 plus 3x minus 3 power. So if I simplify on both sides here, we're going to have 3 to the 4x minus 2 equals 3 to the 3x minus 3 power. Again, now I've written each side as a single exponential with like bases. I can set those exponents equal, so we're going to have 4x minus 2 equals 3x minus 3. And when I solve, we'll subtract 3x on both sides, leaving me with x on the left, and I'll add 2, leaving me with a negative 1 on the right. So here we get x equals negative 1. Okay, we're going to take a look at solving some basic exponentials. They're going to start popping up in a few of our worksheets. But this is the first thing on you're asked to solve an exponential. You should always check to see, can I solve it using like bases? Before you even look at using a logarithm or any other method that you may encounter in terms of solving exponential equations, you always need to check, can I solve with like bases first? Because quite frankly, the work is going to be simpler, it's going to be more straightforward, and it's going to be less messy to deal with, okay? This is like the GCF of quadratics. You always check for a GCF. Here in exponentials, we're always checking, can I rewrite with like bases? All right, have a good night, and we'll see you guys tomorrow.